Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we're going to discuss logarithms, and specifically, how they relate to time complexity. Logarithms can be a little bit intimidating because they're focused on math, but here, we're going to make them dead simple and break them down so anyone can understand it. Logarithms are a very important topic because they're one of the best time complexities. We can see it's nearly as good as constant time. So this makes it essential to understand how logarithms work and how we can apply them in our coding interviews. And specifically, we see logarithms pop up a lot when we're discussing sorting and searching. So let's dive in now and understand logarithms. We can't discuss logarithms without first discussing exponents. Exponents are very much related to logarithms, and in fact, they're the inverse of a logarithm, or a logarithm is the inverse of an exponent. So most people understand this concept. When we say a number raised to a power, here we have 2 raised to the third, it just means that number times itself for this exponent's value. So we have 2 to the third is 2 times 2 times 2, or 2 3 times, which is 8. So exponents mean multiplication. And logarithms are the inverse of exponents, so they mean division. So if we have log 2 of 8, what we're saying is how many times do we have to divide this base, 2, into 8 until it reaches the number 1? And the answer is 3. 8 divided by 2, 1, 2, 3 times is 1. So the key to logarithms is dividing a number up multiple times. We saw the log 2 of 8 is 3, but this is also the inverse of exponents. 2 raised to the 3 is 2 times 2 times 2, 3 times, to equal 8. So if 2 is our base, we could also look at a logarithm as being, what do I need to raise the power of 2 to equal the number 8? And the answer is 3. So the base matches here with the base of the exponent, and then the exponent itself is the answer to our logarithmic equation. So up to now, we've been looking at a base of 2 for our logarithms, but the base can actually be anything. For example, we have a base 10 here, so this says 100 divided by 10 is 1, so log 10 of 100 is 2. Log 10 of 1000 is 3, log 10 of 10,000 is 4, and so on. Or, if we did a log base 5, the log 5 of 25 is 2, because 5 times 5 is 25. So bases can be anything, but typically for interviews we just assume the base is 2 because we're dividing our input in half each time, which signifies a log 2, dividing by 2 over and over and over. So let's visualize what this means and how it actually applies to our problems. Here we want to find the number 16, and we have a sorted array. If we search this linearly, it would take 16 total operations because we would have to go through all 16 items. But we'll implement a binary search, which means we're going to skip half the items each time, or divide it by 2 every time we make a move. So we start at the beginning, we check the middle item, and we see 16 is larger, so we move right. So by going to the midpoint immediately, we've skipped half the items, or divided the input size by 2. Then we go right again, and we take half of the remaining items. So there were 8 left, we divide that by 2, so we skip 4 items this time. Now we've done a total of 2 moves. There are 4 items left, we go by 2 of them, we see 16 is further right, we've divided the 4 total items by 2 again, down to 2 remaining. Then we go right again. There are only 2 items left. We didn't find 16, so we go right one more time. And finally, we land on 16. So it took us 5 total moves, go from the very beginning to find our target, and that's because each time we skipped half of the array and we knew which direction to move because it was sorted. This is going to be much faster than the linear time, which would have to start at 1 and then go through all 16 spots. So let's look at some different input sizes and see how O of n linear time compares to O log n. With an input size of 2, O of n is obviously 2, but then our log time is just 1 because 2 divided by 2 is 1. with an input size of 4, linear stays 4, and log time is just 2 because 4 divided by 2 divided by 2. We have an input size of 8. Then this is just 3 for our log time. And now let's skip ahead. We have this very large number, 1,048,576. Linear time, we're going to have to go through all of these items. But with log time, when you divide it over and over again, it only takes 20 operations. So imagine you had an array with all these items. If you divide it by 2 by skipping half each time, you would reach the item you're looking for in just 20 moves. So this is why log time is so powerful. 20 operations is absolutely nothing, and why it's almost nearly as good as constant time. Even as the input size grows very large, the number of operations still stays very small. So in interviews, the most common way to see logarithms or log time is 1. Binary search, where you search and cut out half the items each time you move. Binary search trees, which are very similar to binary search. It's just an ordered tree where you cut out half the tree each time you go left or right. But in general, you see log time anytime you take an input size and divide it on every move. This division is how you get it so fast. Even for large numbers, when you divide every single time, the number of operations actually still stays very, very small. And that is why logarithms are so important to programming and why understanding how to use them can really improve your time complexity if you have the right conditions. Thanks everyone, and I'll see you in the next lesson.